Chapter 15 Inductors. There are 5 sessions in this chapter. 15.1 Introduction, 15.2 The Applications, 15.3 Different Types of Inductors, 15.4 Factors that affect the capability of inductor, which is called inductance. 15.5 Series and parallel inductors. 15.1 Introduction. Whenever electric current is applied to the inductor, magnetic wave is generated, so this inductor is surrounded by a magnetic field. Since the magnetic field carries energy, the inductor stores magnetic energy. Using this phenomenon, this special feature that inductor has, we build lots of other electronic devices. Here I have a few schematic symbols for inductor. The first one, the blue wires in the middle represent inductor. It also means it's a fixed inductor. Its value won't change. After the manufacturer made this inductor, the values cannot be changed by the user. The second symbol represents a variable inductor. The value can be changed by user, which means the manufacturer intentionally make the inductor this way, so user has the capability to change its value. For many variable inductors, they have a screw on it. To change its value, we can simply take a screwdriver and spin this screw to change its value mechanically, manually. The third symbol represents an iron core inductor, which is an inductor that has an iron core inside the coil. The last one is a ferrite core inductor. Instead of using iron core, we put different kinds of material called ferrite material inside the coil. These materials can enhance the magnetic field. With same amount of current going through this inductor, more magnetic field can be generated due to adding this ferrite material. This is the simplest inductor circuit. As you can see, there is a voltage source, a switch, an inductor connected in series with a resistor. That resistor is necessary, otherwise, once we close the switch, without a resistor, this is a short circuit. Since the ideal inductor is just a piece of wire, it has no resistance. So that resistor here is necessary, is required. Inductance is a measure of the coil's ability to create induced voltage. That induced voltage is the result of changing the current in the circuit. So the key word here is changing. The voltage induced when the current changes. If the current is constant, no induced voltage at all. So you may wonder, oh, we have a series circuit here. How come the current is changing? Isn't the current constant at anywhere? The current changes only at the moment when we close the switch. The circuit becomes from no current at all to maximum current, that is, reaching the constant current at the end in the steady state. Another key thing that we need to keep in mind is this induced voltage direction is always opposite to the change in current. Their directions are always opposite. For example, the conventional current flow out from the positive terminal towards the negative terminal. The induced voltage is in the opposite direction, which means the higher voltage is here at this point. The lower voltage is here at this point. This animation shows how it works. As soon as we close the switch, the electric current starts to flow out from that positive terminal. And then it just continues running, continue flowing through the circuit, and now it enters to that inductor. As soon as this current flows through this inductor, that green arrow which means the induced voltage being created, and the current continue flowing and then return back to the negative terminal. When the current reaches to the end of the terminal, eventually in the steady state, the current becomes constant in the circuit. Induced voltage becomes zero. The unit of inductance is Henry. Henry is the physicist who studied inductors, inductance, and discovered all these phenomena. To give him credit, we use his name to represent the unit of inductance, Henry. The symbol of the unit Henry is just the first letter H. Make sure it is capitalized, is uppercase H. By definition, 1 Henry is when the current goes through the coil changing at the rate of 1 amps per second. Induce 1 volt across the coil. This is the definition of 1 Henry. To express this in mathematical expression, is 1 H, the 1 Henry, equals to 1 amp per second. 1 ampere of current passed through the conductor in 1 second. The unit Henry is a large unit. For most inductors used in the laboratory, or at least the inductors used in most commercial electronics, we don't use this large unit. Millihenry and microhenries are more commonly used. Here has a kit that has different values of inductors in it. If you search this in store, electronic store or online stores, you can easily find this kind of kit. It gives you different values of inductors. If I zoom in this label, the kit has inductors with following values. Here, 1 microhenry inductor. We have a 15 microhenry, 1 millihenry, and 3.3 millihenry inductors, and so forth. This kit is not expensive. At the time I checked the price, it's around $12 to $15. Here shows the energy being stored in the inductor. We know when electric current goes through the wire, instantly the wire carries magnetic field. The total energy stored in this inductor can be calculated by following formula. The work, which is the energy stored in the inductor, the W work, equals to 1/2 times the inductance of the inductor multiplied the current square. The formula shows the energy stored in the inductor depends a lot on the current that passes through this inductor. Inductance plays an important role, but current is more important. The work has a unit of joule. The unit of inductance is Henry, and the unit of current is ampere. Let's look at this circuit again. The circuit has 1 voltage source, an open switch, inductor L, and resistor R. Initially, the switch is open. As soon as we close the switch, the current forms and starts to flow in the circuit. We want to find the total energy stored in this inductor. That is, W equals to 1/2 Li squared. Let's work on this example. A circuit has a voltage source called Vs, connects to a switch and an inductor L with 30 millihenry and a resistor R. The current of 2 amps is applied to this circuit. We want to know how much energy stored in this 30 millihenry inductor. As you can see, we don't know the resistance value, but it is fine, it is okay, we don't need to know it, as long as we know the current and the inductance. The energy W equals to 1/2 Li squared, and now let's plug in those numbers. 1/2 times inductance L equals to 30 millihenry. and multiply the current square, which is 2 milliamps square. If you look at here, millihenry and milliamps, the prefix milli means 10 to the power negative 3. So that is 1/2, 30 times 10 to the power negative 3 Henry times 2 times 10 to the power negative 3, and then the entire thing square. Punch these numbers into calculator, I get 6.0 times 10 to the power negative 8 joule. If I change this number into engineering notation, the answer is 60.00 nanojoule, a very little energy stored in this inductor.